Okay, let's start. Do you guys have any questions? All right, so let's see. So we're still discussing the topic of random variables and basic things we can do with random variables like expectations and variances, right? Now, I guess we mentioned continuous random variables last time. And the main features there, right, is that continuous random variables will have a PDF, right, probability density function, and basically to work with continuous random variables, you need to be able to know how to handle a probability density function very well, as reflected through computation like the max of a n random variables, the distribution, right? If you have x1, xn, right, IID, let's say random variables with density f, right, like that, then the max, right, will have density what? Probability, right? The density of the max will be the probability that, so let's write that down, right? With integral of the density, the common density, right? Like this, raised to n minus 1 times n, and then times the density itself, right? Like that. So basically, to be able to work this out, right, it relies on how to work with the density of continuous random variable itself. But I'm not gonna kind of go more into this unless there's a reason to, because in this class, at least like for the majority of the section, the chapters will be working more with discrete random variables. So we're going to just focus more on the discrete random variables, especially with kind of the modeling aspect, okay? So I'm just going to do more problems to start with today. Problems, I think, on your homework. And then we're going to mention a few more theoretical points, and then do more problems. So to start with, I think we have number 29. Right. So yeah, this is your first quiz. Question number 29. So basically, the problem talks about a sequence, right, of n coin flips. But then, right, you're not looking at the result of the flip itself, but you look at the changeover, right? Or the turnover, I guess. changeovers, right? So basically, when a coin change from, I guess, head to tail like this, right, that count as a changeover. So head, tail, tail, head, tail has 5 changeovers. Right. So 1, 2, 3, 4, and 5, right? Like that. And so I guess this question is also related to question number 36. No, number 40, no, number 41, right? So basically, you look at the random variable x, which basically counts, right, the number of n changeovers. In the n coin flips. Okay. And you're kind of trying to work out the distribution of x. And of course, right, this is like a general question. When you ask for a distribution of a random variable, what can you be referring to? Well, you could be referring to the probability, right? This is a discrete random variable. So you could be referring to probability that the random variable will take on some particular value, right? So here, the number of changeovers can happen anywhere from 0 to n minus 1, right? Changeovers. So that's one thing. Another thing you can be asking for are the moments, right, of the random variable, etc., right? So here, right, number 29 exactly asks you about this. But so here, right, there's one more notation. For each of the coin flip like this, I mean, we assume the independent coin flip, the probability, right, of a coin flip turning head is, just some letter P, right? And in question number 29, you assume that a coin flip is fair, so P is 1/2. In number 41, it's just a general P, right? So basically, long story short, you look at the number of changeovers in n flips, and you try to write down, right, the probability that k changeovers happens. And then for when the coin's fair, and you also want to work out, right, the expected number of changeover for a general P, right? Well, the question of variance and things like that is also valid, but we'll just leave it aside because, as you can see, variance is like it's a more difficult computation, okay, than expectation in general. So sometimes we can do it without, much trouble. Sometimes it's a lot harder. Anyway, so for your quiz, all right, let's try to ask you to solve for this question, right? So when p equals 1/2, find the distribution, right? What's the probability of having k changeovers, where k ranges from 1 to 0 to n minus 1? How would you do this? Any answer here for this probability? So in general, right, if you have a general P, that P is not 1/2, then this question might be difficult to deal with because, you know, having a changeover from head to tail will be a different probability, for example, right, from having a changeover from tail to head, for example. But when P equals to 1/2, right, what happens is the following. So when you have P equals 1/2, then basically, first of all, P equals 1/2 means any sequence, right, all outcomes, right, of the coin flips are equally likely. Okay, because the coin's fair. So basically, we can approach it from by counting. Okay. Again, right, if P is not equal to 1/2, then having this sequence will be different, for example, right, from having this sequence in terms of the likelihood, right? Because the likelihood of tails is not the same as the likelihood of heads. On the other hand, both of these have 5 changeovers. So that makes it more difficult to deal with this question when P is not equal to 1/2. But when P equals 1/2, for example, then this sequence and this sequence have the same probability. They're both equally likely. So we just count, right, the number of changeovers, number of possible changeovers. Well, so actually to start with, right, how many outcomes are there in n coin flips? How many outcomes can we have in n coin flips?
Is it just n-1?
No. Well, what do I mean by that, right? Suppose we have 3 coin flips. How many sequence of 3 coin flips can we have? Head, head, tail, head, tail, 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 things like that, right? How many ways can I do it?
Is it 6 ways?
No. It's 8, right? It's 2 cubed. I can do it 8 ways, right? So in general, I can do it with 2 to the n possibilities, right, for the n coin flips. Okay, so that's my sample size. I will divide everything by 2 to the n. I mean, I would divide the possibilities of changeovers. So if I want k changeovers, right, how many ways can that happen? How many sequence will give me k changeovers? For example, right, go back to the 3 coin flips. If I want, so there are 8 possibilities. How many sequence give me no changeover? This should be an easy question, right? in 3 coin flips, right? Actually, in all coin flips, how many sequence gives me no changeover? The answer should be 2, right? Because which sequence has no changeover? Has heads and tails. All other sequence has some changeover, right? How many sequence gives me 1 changeover? In fact, right, I think that might be a little bit harder. Doesn't matter. How many sequence gives me 2 changeover? Should also be 2, right? Which ones? Head, and tail, head, tail. Well, the remaining 4 would be what? 1 changeover. Which ones? Head, tail, head, tail, head. What else? Head, tail, right? These all give me 1 changeover. So if we have 3 coin flips, then the probability of no changeover is 2/8, 1/4. 2 changeovers also 1/4. 1 changeover is a half. Understand? So that's counting, right? With 3 coin flips. With n coin flips in general. And then with k changeovers. How many ways can we do it? This is k, right? K equals to 0, 1, and 2. And here n, right, is equal to 3. Well, the answer is going to be n minus 1 choose k times 2. Okay. Why is that so? Well, let's see, right? First of all, let's try to see if this formula works for this example. So n equals to 3, right? So when k equals to 0, that's 2 times 2 choose 0, which is correct, right? And then when k equals to 2, that's 2 times 2 choose 2. When k equals to 1, that's 2 times 2 choose 1, right? So, but in general, why is this formula true? In general, right? Basically, okay. So first of all, do we understand why there can only be 0 to n minus 1 changeovers? Right? Why can't there be n changeovers, for example? Because it takes 2 coins, right? 2 consecutive coin flips to produce 1 changeover, right? So therefore, it's like kind of like the gap, right, between the coin flips, if you will, right? So the space between the coin flips, whatever, right? But it takes two consecutive flips to produce 1 changeover. So that's why it's the n minus 1. And it's that n minus 1 right here, right? So basically out of n minus 1 possible, let's say, gaps, right? By gaps, I mean the location, right? Between the coin flips, you choose K position, right? For the flips to happen. Right? For example, let's say when n equals to 4, right? Then you have like 3 possibilities, 3 places, right, for gap to happens. And let's say you want 2 gaps. Sorry, two changeovers, right? That means out of these 3 places, you choose 2 for changeovers to happen. Let's say you choose here and here, right? There's 2 places for changeover to happens. All right, but what else? What does this 2 means? Now you have to fill it in, right, with head or tails. Let's say if you fill it in with head, then because you require changeover to happen here, this must be a tail. And then you say there's no changeover, so this is a tail. Finally, you say there's a changeover, so that's head. That's one way. Or you fill this with a tail, then you require changeover to happen, so it's a head, tail. So this is the 2, right? 2 possibilities to start the sequence. Okay. And then there are 2 possibilities to start the sequence. You understand? Flips. And that's it. Because once you decide what the starting flip is, then by deciding where the flips happen, then the whole sequence of coin flips will be determined. And that's why it's 2 times n minus 1 choose K over 2 to n. And that's exactly the probability of n coin flips. Sorry, K changeovers in n coin flips.
Why do we multiply it by 2?
Again, right? It's the 2's right here. Once you decide for any kind of changeover, once you decide where the changeover happens, then there are 2 ways to have those changeovers, right? Here. For example, here are 2 sequences that have 5 changeovers with exactly the same location where changeovers happens. You understand? Basically, you flip head to tail, you have the same sequence with the same number of changeovers happening at the same location. That's what this 2 is about.
Why the denominator is 2n when the numerator is about choosing k gaps between n minus 1 gaps?
So again, 2 to n, what are we counting? We're counting the number of ways, right, for something to happen out of the total number of ways for things to happen. So again, right, with 3 coin flips, how many sequence of coin flips can I write down?
8.
Out of those, how many of them have no changeover?
2.
Which is 2 times 2 choose 0. So the probability of no changeover in this particular case is 1/4. But the general answer is that, right? It's just basic counting, right? You count the number. It's just like how you define probability, right? Again, right, the key is because everything's equally likely. If things are not equally likely, then by counting like this, right, the division by 2 to n. Well, here's another way you can see it. Division by 2 to n is like 1/2 raised to n power. And here it's just basically, right, the probability of each coin flip raised to n by independence, right? So you can see it that way. But yeah, so 2 to n is a total number of ways that you can have coin flips. These are the total number of ways for you to have K changeovers. All right.
Thank you.
Any other question? So once again, right, this is easy or doable when P equals to 1/2. You should really contemplate what happens when P is not 1/2. Then my counting argument still works. Like the number of ways for flips to happen, for changeovers to happen is still this. What really changes is the likelihood, right? Actually, so this 2 right here is still true. But as I say, right, there are 2 ways for the number of changeovers to happen with exactly the same number of changeovers at exactly the same location. However, the crucial difference is now these 2 sequences do not have the same likelihood because tail and head don't have the same likelihood anymore. And therefore, right, even though counting is still done the same way, the way we calculate the probability will not be the same. Therefore, the final answer will not be like this. It will be much more complex. Because now you have to distinguish. Well, I guess it's not much more complex, but you will have to distinguish one sequence from the other, right? With general P, you have to distinguish one sequence from the other. You just have to add, right? The probability of this sequence happening, and then the probability of this sequence happening. That's what this 2 is about. You don't have this 2 anymore. You have one sequence of changeovers and another sequence changeovers where they are the same. They just flip head to tail. Anyway. All right. So now question number 41 now asks you for the expectation, right, of this random variable. Okay. And so number 41, and this is for general P, right? For general P, find expectation of X. So I guess it can be done in several ways, maybe. One way is to recognize what distribution X can have. But one trick, right, is that we're dealing here with general P, not, right, just P equals 1/2. So maybe, right, the question is like this. So how do we find expectation in general? We find expectation in general by breaking, right, the random variable down to a sub. So what are these xi? And what are we summing over? So when we want to find the expected number of turnovers, right, total number of changeovers, what can we break it down into? We can break it down into the individual changeovers, right? So basically, we can sum this from 1 to n minus 1, where xi is, so this is counting, right? Indicator 1 if a changeover happens at, let's say, gap, right? I and 0 otherwise. Right? Well, what do we mean by gap I? This is gap number 1, gap number 2, gap number 3. Right? If there's a gap there, we add 1 to it, and we'll get the total number of gaps. Right? And so expectation of x then, you see, is the sum of expectation of xi. Well, the question is, what is expectation of one single xi? If you pick any gap, what's the probability that a changeover happens at that gap? For general P. And the answer is 2 P 1 minus P. Right? How so? Oh, easy, right? Well, if you select any gap, then the only way for a flip to happen is one of them is tail, one of them is head. There are 2 ways to do that. So that's the probability. Right? Remember, for a indicator function, right? So maybe this will help. Expectation of an indicator function is a probability, right? That it happens. So, right. So therefore, this will be n minus 1 times 2 p1 minus p. Any question? All right. So let us move to the next one, which I believe is question number 44, say. Where it's actually related to, right, to question number 43. Where, what was the question? The question was, right, you have an urn containing n plus m balls and reds, m blacks. Okay. Let me write down. So you withdraw, right? One ball at a time, right? Without replacement. Like that. And you are interested, right? At least, so in question number 43, you're interested in the number of reds before the first black. Okay. And in particular, you're interested in expectation of x. Okay. So can anyone remind me what the answer here is and what's the reason?
It's 1 over the number of black balls plus 1.
But that's not X, right? That's the individual, right? So that's not X. That's XI. What was XI? So, right, you remember one of the details, right? I think you remember this one. What are the XIs? So what are we counting over? What are we counting over to get the number of reds before, the total number of reds before the first black? We're counting over the red balls itself, right? So we look at each red balls and we say that it's 1 if the ith ball, right, is before the first black, and 0 if not, right? So we look at each red balls and we see if it's before. So this is let's red 2, red 6, and red 1, 5, right? Like that, right? So if this is the case, then there are 3 red balls, right, before the first black. And the indicator function, the x2, x6, and x5 will be 1s. All the other xi's will be 0. And 1 over m plus 1 is the expectation of the xi, right? Well, what's the reason? The reason is when you focus in on any particular red ball, and you're concerned about how it's compared to the blacks, then the other reds are irrelevant, right? You just look at the relative positioning of the red with the black itself, themselves. In which case, right, there are a total of m plus 1 positions, right? M for blacks and 1 for red. They're all equally likely, right? So there's one position out of m plus 1 positions for the red to take place that's in front of all the blacks. So it results in 1 of m plus 1. Okay, but that's not expectation of x. Well, expectation of x will be n times that, right? By linearity of expectation. Okay. So that was the answer for 43. Any question about that one? So question number 44 is a repeat, if you will, of this question, but now they let y be the number of reds between the first and the second black. Okay. And they ask you to find expectation of y. And so, for example, I mean, if it literally, right, like this, then the number of reds between first and second black would be 0, right? The way I draw it. But if you supposedly, let's say, like that, right? Then there'll be 2 red balls, right, in between the first 2 blacks, for example. But in general, how many do we expect in between the first and second black? And why? So again, right, you should not be surprised that the theme of all the questions you see, I mean, not all, but a lot, is you try to, when you find expectation of something and even variance, that's what you see soon, you try to break it down to a sum, especially with counting, because if you look at a total number of something, when you are able to break it down to a sum, then somehow the individual term can be much more easily handled in terms of expectation, right? So the question is here, what can we break, right, y into and why? Well, the answer is you break it into exactly the same thing. I mean, almost the same, right? As the previous one. So here, right, the difference is instead of counting a success, a 1, if the ith red ball comes before the first black, and you count as a success if the ith red ball between, right, the first 2 blacks. And 0 otherwise. You understand? So for example, right, in this sequence that I draw, then y2, y6, y5 will be 0 because, right, you only count it if it happened between the first 2 blacks. y7, y8 will be 1, resulting in 2 red balls in between the first 2 blacks. All otherwise will be 0. Okay. Now, what is expectation of a yi like this? What is the expectation of a y like that? The answer is still 1 over n plus 1. No difference. Okay, why so? Because again, the argument is actually exactly the same. Suppose you focus on R7, let's say, right? Then you ignore any other reds because they're irrelevant. You only care for the position of R7 relative to other blacks. And you can see, right, out of m plus 1 position that R7 can take, there's only 1 position that lands it in between the first and second black. Therefore, it's 1 over n plus 1. Therefore, expectation of y is n over m plus 1. Exactly like the previous question. So 44 and 43 have the same answer. And then, of course, right, the textbook asks if you think this is a surprise or something like that, and asks you to explain why. The answer works out that way. What they really mean, right, of course, it's not a why because the y is right here, but why is more like intuitively, why do we expect this to happen and we don't see it as a surprise? Well, the reason is basically, right, if you look at it, the general theme of 44 and 43, and you can generalize it to, more like this. Basically, you look at a number of reds in between the blacks in general, right? So you think of the black as a marker, right? You remove one ball at a time, right? And basically, the black is a marker, right? And you basically count the number of, let's say, reds in between these markers. And if you think about it, right, first of all, these are not independent, right? So for example, I'm not trying to say X and Y are independent. So if you have a lot of reds, right, before the first black, clearly there cannot be too much red left in between the first and second black, right? However, marginally, or what we're saying is if you have no information, right, you don't know anything, then the number of reds before the first black, or the number of reds in between the first two blacks, or the number of reds between the second and third black, they all have the same distribution. Meaning you will say that the probability they take on any value are similar because there's no difference, right, in between the first two blacks, so that's between the second black and the third black. In terms of how many red balls can be in between these, they're all similar. They're all the same actually. And that's why they have the same expectation. They would have the same probability distribution as well, even though it'll be hard for us to write down what the distribution is. That's why we're not writing it. But they have the same everything, same variance, same expectation, same probability distribution. The only thing, right, is that they are not independent. That's what they're not about. Okay, any question? All right. So now let's continue to question number 58. Here it says, an urn contains, I guess, 2 end balls, R of which are reds. Okay. And the balls are randomly removed successively in pairs. So basically sorry, let me just say not in pairs, because that might give a wrong impression. 2 at a time, right? So basically there are 2 N balls, and so many are reds. Notice that, right? So this is an even number, like you have 4, 6, 8 balls, whatever. But the number of reds, right, can be an odd number. Maybe out of 10 balls total, you have 5 reds, right? That's fine. And you remove, right, the balls 2 at a time. And you notice, right, that X be the number of pairs where both are red. Okay. So you remove ball 2 at a time. And then if a pair is red, you note it, right? And you look at the total again, right? The keywords, the total number of pairs of both are reds. Of course, the question is about, let's say, first expectation, right? What is the expectation of X? And so, again, the key is about expressing X as a sum of random variables. What are they? And how can we find the expectation of the individual term? I'll be right back. All right. Can anyone tell me how can we write X here as a sum of some random variables? And then how can we find expectation of such random variables? So it should be clear, right, that since we're kind of tracking the pairs of reds and the n pairs total, right? Then we will sum from 1 to n, because we're gonna draw balls 2 at a time, so there are n pairs, right? Will be drawing out. So xi will be 1 if the ith pair, right, has both reds. So that's a success, right? And 0 otherwise. Okay. And then expectation of xi will, of course, right, be the probability that the ith pair has both reds. Now, what is this? What's this probability? All right, so this is just a counting argument. You're focusing on, I mean, you know, two, right? Two balls out of two n balls, whatever they are. So there's a possibility of 2n choose two ways, right, for that to happen. Okay. Now, out of these 2n choose two ways, how many ways for them to be both reds? Well, the answer is R choose two, right? Because you must choose both of them from the red collection. R of them is reds. So therefore, that's the problem. That's the expectation. And so then, right, expectation of X then being the sum, and by linearity of the sum, right, it's going to be n times that number. Any question? All right. So that should cover it for some of the questions on the homework. Now, let us kind of say a few things about the topic of variance, right? Well, I mean, we talked about variances before, but let's just talk about a few more details about variance, right? Or, you know, kind of go more in depth about it. So variance, by definition, right, is the following. So it's the mean square error, right, of X away from its mean, right? So it's the sort of like the average distance, right, of X away from its mean. So it measures the spread, right, of a random variable. So that's the meaning of the variance. But as far as computation is concerned, it's the second moment minus the square of the first moment. But for this reason, right, exactly for this reason, variance is not, right, linear in general. So we'll talk more about it. But one of the, for example, right, the hallmark of expectation, for example, is the expectation of a sum, right? Notice that's what we've been using a lot in the problem so far, is that the moment we break a random variable down to individual random variables, and we find the mean of the individual random variable, and we just sum it up. We don't care about relationship between the xi's in terms of independence, right? These xi's here clearly are not independent, for example, in this question, right? Why? Because if you have a pair of reds, right, somewhere, it will decrease, right, the likelihood of a pair of reds happen somewhere else, because these are removed without replacement, and there's only so many reds, right, in total. But expectation, again, right, doesn't care in terms of the sum, right? It's always linear. So expectation of x is a sum like that. On the other hand, variance, right, won't work like that. But here we're just going to be, let's say, specializing, right, to a case of a constant, interaction with a constant. So here C is a constant, right? C is not a random variable. So expectation of C times X is C times X, right? But variance doesn't work that way, right? Variance of X plus C is what? And variance of C times X is what? This is question 50, right? Which is on your homework. So this is quiz number 4. Right? What is variance of X plus a constant? And what's the variance of constant times X? And why? So what's variance of X plus a constant? Like X plus 2. What's the variance of X plus 2? Now the answer is it's the same, right? It's variance of X. It's not like this. What about X, variance of C times X? It will be C square, right? Times variance of X. Again, right? Not like this. And so even at the level of interacting with a constant, then variance already behaves differently than expectation, right? So how do we prove this? Well, for example, right, how do we prove that variance of X plus C is equal to variance of X? Or you have nothing better to do, right, than to use the definition. So that's going to be expectation of X plus C squared minus the square of the expectation of X plus C. Expectation of X plus C squared, right, is expectation of X squared plus 2XC plus C squared, right? So notice here I'm expanding the random variable. Here I take expectation of X plus C and then that's squared. So it's going to be expectation of X plus C, the whole thing squared by the linearity, right, of expectation. Okay. But either way, right, this comes out to be same thing here, right? And you see, right, these two cancel, leaving you with which is exactly the variance. All right, any question? This is the same, right? But much easier. So I'm going to skip. But right, you can just do the same thing, apply definition, and you see that it's straightforward C squared variance of x. Now, what we want to highlight here, right, is not even these formulas. You should know them, right, by heart, and prove them very quickly. What we want to focus on is, if variance is not linear in general, and when it comes to, right, especially this expression, because we'll be dealing with sum of random variables a lot in this class, then how do we handle it? So in general, right, variance of a sum will be the sum, right, of the variances, and then plus the covariance terms. Like that, right? And so when you compute, right, variance of sum, not only you have to calculate the variance of the individual terms, you also have to calculate the covariance before you can, right, add them up. And so, well, anyway, right, so you only have basically the simple formula, right, where variance of sum is the sum of variances, the covariance vanishes, right? So this is enough to have the variance of the sum equal to sum of variances. So this basically means the xi's have zero correlation, right? Something like that. The xi's have zero correlation. But a lot of times you have independence assumption, right? If they're independent, then that will work. So, but of course, right, in general, you don't have this, like this particular example, right? The xi's here, as I explained, are clearly not independent. A lot of problems we do are not independent, right? So you have to work with a more general formula. And so let's talk about what the covariance term means, right? Or how to compute the covariance. The covariance of a pair of random variables is expectation, right, of, so the definition is basically the cross term. So like this. All right, this is the definition. On the other hand, right, you can simplify this down to this. So this is the computational formula. And so, well, a lot of times, right, computation of the covariance is not easy, exactly because of this kind of product. Okay. So, however, if, and this is the case that you will see a lot in this class, and especially in chapter 2, and maybe chapter 3 as well, is that if both of the xi's and xj are indicator functions, right? In other words, xi equals to 1 if something happens. By EI, I mean just some event, right? Some event EI happens, and 0 otherwise. same as xj, right? Xj will be 1 if some event happens and 0 otherwise. Then xi, xj represents 1. If you multiply two indicator function, what do you get? What do you get when you multiply two indicator functions? Well, if you multiply ones and zeros together, right, you still get ones and zeros. So it's still 1 and 0. But it's 1 when what? 1 if both, right? It's only 1 if both of them are ones. But both of them are ones if EI and EJ happens. And 0 otherwise. So basically, when you multiply indicator function, you're looking at the AND operator, right? If this indicates something and this indicates something, then xi times xj indicate the indicator. So xi times xj is also an indicator function, but it indicates the intersection of ei ej. All right, that's what it does. And let me say it's not even an indicator; it's the indicator. All right, of the intersection. So therefore, if you have to calculate the covariance term, you would end up basically calculating basically the probability of EI-EJ happening. And that's how you would work out the covariance or the variance question in a lot of the problems in chapter 2, right? Including, for example, this question, right? Number 58 actually has two parts, right? The first part is about expectation. The second part is about variance, right? Anyway, right, so we're going to go over those problems, but I'm going to pause here to see if there's any question. Okay, so before we do this, right, let's maybe go back to question number 56, which is on the homework of last week, which we didn't go over, right? I think last time. So what was it? So this is the coupon problem, right? All those coupon problems. So you have n types of coupons. All right. But before the coupon question we did, all these types happens equally likely, right? But now the types are not equally likely anymore. Each type, type I, let's say, right? Each coupon can be of type I with probability pi, right? Where the sum of pi is 1, right? When you sum over all the types. And now you have a collection of k coupons, right? And and you let X be the number of different types, right? In this collection. And you're interested in the expectation and the variance, right? So, of course, right, the question to be discussed here is variance. Expectation should be easy, but let's make sure that we know how to do the easy problem too. So this is quiz 5. Find expectation of X. So we must break X down into components, right? As a sum. What are the xi's? Well, so X is a total number of different types in the collection. So you just basically then, right, clearly you go through the type, right, and say that is 1 if type I, right, is present in the collection and 0 otherwise, right? Now, what's expectation of each of these xi then? So expectation of each of the xi is the probability, right, that type I is present in the collection. Right? What does that mean? That means that at least, right, one of the coupon must be of type I, right? At least one of the coupon must be of type I. But whenever we deal with like a at least question, right, that means 1, 2, 3, etc., right? And numbers like that is possibly easier to look at a complement. So you look at 1 minus the probability that type I not right in the collection. And this will be 1 minus what? So each coupon, right, can be of type I with probability pi. So all coupons must be not of type I. Right, there are k coupons total. So that's the probability. Okay. And then of course, expectation of x will be the sum, which is this sum. Okay, like that. So notice, right, before when we sum like this, a lot of times we just multiply with n, right? Whatever that answer is, we just multiply by n. The reason is because a lot of these problems we've done before, all the xi's have the same expectation, right? That's why we multiply by n. On the other hand, right, here, the xi's do not have the same expectation because the pi can be different. And so that's why there's no such thing as reducing the sum to a multiplication. All right. But of course, right, the real question is about the variance. So let's see, right? To find the variance, again, right, we must use the same structure. So the variance is a sum of the variances plus the covariance terms. So there are two things we need to compute. We need to compute the variance, and we need to compute the covariance, right? So let's see. Can you compute the variance of the xi's? Okay. So what's the variance of the xi's? So remember, right? If x is a Bernoulli random variable, then expectation of x is p. What's the variance of x? Variance of x is p times 1 minus p, right? And so whatever, right, the expectation of x is here, which is this number, then we just have to multiply it with 1 minus that, and we get the answer. So we can say something like qi times 1 minus qi, right, where qi is 1 minus pi. It's a k power. Okay, so far. So that's the easy part. The more challenging part is the covariance term, right? What is this term? Or, right, let me just make it even more direct. So covariance will be expectation of the product minus the product of the expectation. We have found, right, this product here. Oh, sorry, these terms here, right? So this is just QI, QJ, right? Where QIs are like that. So the real challenge is just this term. So the quiz is about calculating that. Okay, so what's the answer here? Or how do we do it? So remember, right? If you have xi, xj being indicator functions, which is the case here, right? Then expectation of xi, xj is just a probability of the events that xi, xj are referring to happening together. And so here, right, xi is the event that type I is present in the collection. So excitation of xij here is just a probability that both type I and type J are in the collection. Okay. And how do we calculate this probability? So here you have to be careful, right? Let's switch to the notation of probability of events. So we're looking at probability of the intersections, right? Where I guess EI refers to type I in the collection. EJ refers to type J happens in the collection. So how do we calculate the probability of intersectional event in general? Is it equal to this? Yes or no? the answer is no, right? Not in general, not unless these guys are independent, right? Because if that's the case, then the answer here will clearly be Qi times Qj, which when you plug in here would make Xi Xj to have covariance 0, right? And remember, type I and type I in Xi and Xj refers to type I and type J being present in the collection. And they cannot have 0 correlation. What's the reason? Well, one simple reason, right, is that if all coupons are of type I, then clearly, right, then type J cannot be in the collection because all coupons are already of type I. So therefore, that type I and type J being in the collection should not have 0 correlation. Anyway, right? The answer is no, right? So if we cannot, like, just use the, like I said, a common mistake, right, from the students to multiply the product of probabilities, what can we do? The only thing left for us to do, okay, is to use the inclusion-exclusion formula, but in the reverse order, right? Okay. Because, right, inclusion-exclusion formula says this is equal to this plus this minus that. But here, this is what we're trying to calculate. All right, so by inclusion-exclusion formula, this is Qi plus Qj, right? Because Qi is the probability type I happens in the collection. And then subtracting what? Subtracting probability of either type I or type J being in the collection, right? But guess what? Again, right, what's the language here? Either type I or type J in the collection means, right, at least one of the card must be of type I or type J, okay? Again, the language is at least one of the card must be of type I or type J. But at least, again, refers to what? 1, 2, 3, etc., right? Which is a lot to count. So we still have to do the complement, right? Which is what? The probability of no card, right? So both type I and type J not present in the collection. Is that okay? So again, right, pay attention here. It looks awfully like the negation of this, right? But that's not really true. Negation of type I and type J not in the collection are, so the negation of this statement will be either type I or type J not in the collection, right? Not both. Here we're saying both type I and J are not in the collection. Okay, so this again, it should not be that hard, but it's a little bit kind of subtle to do it precisely. And these are the right steps. And so finally, right, this will be Qi plus Qj minus, right, 1 minus. So here, basically now we can just go through each coupon, right, and make sure that it is not of type I or type J. So that's going to be 1 minus Pi minus Pj raised to the K power, like that. All right, any question? And that's it, right? Basically now then you just plug these numbers, however ugly they are, into this formula. And that's your final answer. Okay. And so unlike expectation, where you tend to have like a nice compact formula, variance, a lot of times it's a mess. Well, what do we mean by a mess? A mess is like the sum here doesn't simplify to anything, right? The sum is the sum. Okay. The covariance is even worse. It'll be this guy minus that product. I mean, I guess it's not too bad, right? And then you sum it up. But that's it. Nothing more you can say. So to recap, right? For the variance calculation, is about stating this formula and then stating what the individual terms are. And that's all you can do. Don't expect anything like a nice formula, right? Nice compact formula for the final result. Any question? All right. So then let us look at the next one, which is the balls removed in pair, right? Where was it? Question 58. Yeah. Right. So let's remind you. So an urn contains, right, 2 end balls, R of which, right, are reds. Okay. So 2 balls, right, are removed at a time, right? Of course, without replacement. Okay. And you let X be the number of balls, the number of pairs, where both balls are reds. Okay. So we have, right, found expectation of X, which let's remind ourselves. So, okay, we can do the whole problem again, right? So X will be the sum of Xi from 1 to n, where Xi is the indicator if the ith ball, right? Sorry, the ith pair has both reds. Okay. And then expectation of Xi, which is the same as the probability of the ith pair having both reds, will be 2n choose 2, right? Because that's a total number of possibilities to pick a pair out of 2n balls. And then the top is R choose 2, which is the possibilities, number of possibilities to choose 2 balls out of the R red balls, right? And so expectation of X is just n times that. Okay. But now what we're after, of course, is the variance. So again, write down the variance. All right. And so what quiz are we on? Quiz 8. So all you have to do now is to list out what the variance term is and what the covariance term is, and you'll be fine, right? So quiz 8, find variance of Xi. Okay, so what's the answer here? What's the variance of the xi's? Well, the xi being indicator function, right, of Bernoulli, again, then, right, so the xi's are Bernoulli p, where p is exactly this number, right? So therefore, the variance, again, is p1 minus p, where p, right, is r choose 2 over 2n choose 2, okay? So again, variance usually is very straightforward if you have an indicator function, because it's just p times 1 minus p, where p is, right, the expectation, which is also the probability of success. Oh, the harder thing, right, is this guy right here. So again, right, covariance is about expectation of the product minus the product of the expectations. And we already know what these are, right? This is just p squared, because they're both the same. So the key question is what is this? All right, so how do we do this? So again, right, expectation of xi, xj is, right, the probability that both events indicated by I and j happen. And what's the event? The event is the ith pair has both reds. So this one will be the probability of both I pair, right, and j pair have both reds, right? Okay. So both I pairs and j's pair are completely red. All right, what's the probability of that happening? So you're removing, right, the balls two at a time. So if you focus on the ith pair and your jth pair, the number of ways you can do that is what? 2n choose 2, right, for one of the pair. And the remaining pair would be 2n minus 2 choose 2, right? That's a number of possibilities for you to draw, right, balls into two pairs, I and j. And now how many ways can them both be reds? Well, it is R choose 2 for the first pair, and then R minus 2 choose 2 for the second pair. Right? And that's it. That's exactly the expectation of the product. And the covariance term is just whatever this is minus this squared. I mean, I guess here you can simplify something because there's a common factor here, but it won't be anything that nice. And then the variance is just n times that, right? Plus 2n choose 2 times that. The reason why, right, we can replace the sum here with n choose 2, things like that, is because here the covariants are all the same, right, for ij. But in general, right, I don't think it's going to reduce to anything that a nice compact formula. All right, any question? Okay, so that should be all. Well, whatever, enough, right, for your homework. Now, the next topic we want to mention in chapter 2 is the moment generating function, right? Or also referred to as MGF, right? Moment generating function. So let's start with the definition, right? If x is a random variable, then the moment generating function of x, denoted as phi sub x, right, at a variable t, will be by definition the expectation of e to tx. Okay, like that. For example, right, the moment generating function of a Bernoulli is what? Well, it's going to be, right now, we just list out e to t times 1 times p, e to t times 0 times 1 minus p. So it's going to be p e to t plus 1 minus p, right? So now, what's the use of moment generating functions? I mean, one of the use you can do with moment generating function is to literally, right, generate the moments. How? For example, right, if you differentiate this function once, well, what is that? Well, you can pass the differentiation inside the expectation, and you're differentiating with respect to t, right? So the x comes down like that. And if you let t be 0, so if you plug in 0 here, then that's expectation of x, right? So on and so forth. Meaning that you can differentiate the moment generating function so many times, like 10 times. And you plug in t equal to 0, you get expectation of x to a 10th, right? Let's say e to the n. Right, so this, you know what? Let me just skip that notation. This is the nth derivative, right? Of the moment generating function. Plug in 0 will be expectation of x to n. So if you know the moment generating function, you differentiate it, you will get all the moments. But that's not a real popular application. It's a possibility. But the application here that we're talking about is to identify, right, the distribution of a random variable. The reason, right, is because the moment-generating function is literally the Laplace transform of either the distribution function or the density function of a random variable. And if you have taken like a course like Math 421, then you would know that if you know the Laplace transform of a function, you can figure out, okay, the Laplace, the original function. Well, by figure out is like quote, because sometimes there's no formula to figure it out literally. But basically the Laplace function, the Laplace transform of a function is unique. So if you know two functions having the same Laplace transform, they must be the same functions, right? So in other words, if you have a random variable, you don't know what that is, but you know this is this moment-generating function, then it must be a Bernoulli random variable. Okay. So for example, if phi of x is p e to t plus 1 minus p, I don't know anything about x. I just know that it's moment-generating function like this. Then I know for sure that x must be a Bernoulli p. Okay. So how is this useful for us? It's useful, let's say, to conclude that certain sum of random variables must result in certain thing. Okay. For example, is an important identity that we'll be using a lot in this class. If you have x1 being a Poisson lambda 1, x2 being Poisson lambda 2, and they're independent. Then the sum will be Poisson lambda 1 plus lambda 2. Okay, so this result can be compactified as the sum of independent Poissons is a Poisson random variable. Again, you should appreciate the fact that you don't always sum random variables to end up being the same in the same family again. All right, we'll talk more about this on Friday. But for now, right, in the last 5 minutes, let's show you why this is true using, right, moment-generating function as a tool. But of course, if we do that, then we must know the moment-generating function of a Poisson. Does anyone know what that is? Or is expectation of e to tx, right? Which will be e to tk, e to minus lambda, lambda to a k over k factorial, k runs from 0 to infinity. Well, you can pull e to minus lambda out, sum remains. Now, is lambda e to t raised to k power like this? And this is a sum, the Taylor expansion, right? The Taylor series of the exponential. So that's going to be like that. Okay. So that's the moment-generating function of a Poisson random variable. And so now, right, we know that x1 and x2 are Poissons. That's the hypothesis. Therefore, we know that xi, the MGF, right? Is like that. Now we need to figure out the MGF of the sum, right? And show that it's of the same form. So how do we do this? So we do the same thing by definition, but exponential of a sum is the product of exponentials. And random variables being independent means that you can split the excitation. But these are nothing but the moment-Yang functions, right, of the individual. But then you see, right, now again, using the fact that product of exponentials is this exponential of the sum, gives us this. Which, right, is exactly this structure, but with lambda being replaced by lambda I plus lambda j, from which we can conclude that xi plus xj must be a Poisson random variable with that rate. Any question? All right, so I think we're right about time. So we'll continue, right, with moment-Yang function and, some of random variables next time in terms of distribution. And then we'll continue on to chapter 3. All right. If you have any question, I'll answer them. If not, I'll see you on Friday.
Hey, I just forgot to submit my the after class attendance quiz on Friday or on Monday, I think. Is there anything I can do about that?
Well, you should have sent me that question much earlier than asking me it right now.
Okay.
So send it to me in email and I'll see what I can do.
Okay, thank you.
Mhm.
Quiz 4, number 50.
Sorry, say again?
Can you please scroll up to quiz 4, number 50? I just want to make sure I copied down everything.
All right. Quiz 4.
Mhm. Yep, right here. Thank you.
Mhm.
I got everything. Thank you so much.